So the next topic we are going to study is velocity. Velocity is a vector quantity, and as we all know that vectors have two things, direction and magnitude. So whenever we will be writing any vector, we need to write its direction and magnitude. Now let us go back to the last topic that we did, displacement. And here the object was moving along this path, and P and P dash were the positions at time t and t dash. Now we have the formula for the average velocity. We know that average velocity is equals to displacement upon corresponding time interval. Now, in terms of symbols, we'll write velocity as the velocity is a vector, so I will put an arrow on it, and then as it is average, so I will put a bar. Now displacement vector we already know is written by delta r vector divided by delta t. As time is a scalar quantity, so we are not putting vector symbol over the t. Now this was our equation 1, so we'll put, and this is our equation 2, so we'll put r in terms of displacement on x-axis and y-axis. So it will become delta xi cap plus delta y j cap divided by delta t. Now this delta t can be distributed below delta x and delta y. Now this is the displacement along the x-axis in time delta t and displacement along y-axis in delta t time. So this is the component of average velocity component along the x-axis, and this is average velocity component along the y-axis. So the important thing here is this, one of the tools that we need to remember, that I have vector on right hand side, so definitely I will have vector on the left hand side also. So this is my right hand side, this is my left hand side, and here I have positive sign. So if the sign is same, it means the direction of velocity vector is same as direction of displacement vector. So this is due to both have the same sign, so then the vectors will be in the same direction. It can be any vector, but if they have the same sign, they will be in the same direction. So it means this was the direction of delta r, so same will be the direction of delta v. So we have, now the important thing is that, as I have discussed, that vector has direction and magnitude. So this is my vector. Now what will be its direction and what will be the magnitude? So of course, if we have, let us draw the components of velocity. If I am taking this as Vx over here, this is Vx, this length, and this length is Vy. So because these are the magnitudes and this vector, but I am interested in velocity. So I will complete this parallelogram. So this distance also Vi, and this distance is this Vx, this is Vi. So this is Vx and this is Vy. And the diagonal, this diagonal, the length of this diagonal is V, and this is my resultant V vector. So this is Vx and this is the magnitude, and if I want to describe this as vector Vx, so here I am adding these two vectors and this is the resultant of this vector, and opposite of it is, if I am writing V as this, so we also call it resolving the vector. So I am resolving V along x-axis and y-axis. So I am interested in what is the magnitude of V. So we can simply see that this is hypotenuse of right angle triangle. This Vx, this Vy, so this is also Vy. So the magnitude of the velocity will be, that's equals to, so hypotenuse is equals to under the root perpendicular square plus base square. So that's Vx square plus Vy square. So this is the magnitude of the velocity. So Vx is the magnitude of velocity along x-axis, Vy is the velocity of magnitude along y-axis, and if I want to write it as a vector, then this vector is Vxi cap. Now this is a vector, and this is Vj j cap, this vector. So in this vector form it is, and this is average velocity. So I will be writing over here as average. So this is the average velocity that I have calculated. Fine. Now my target is to find the direction. So direction will be, so direction is, I always write it as theta along the x-axis. Now if this is the base and this is the hypotenuse, then we know that tan theta is equals to, we have already written it over here. So tan theta is equals to, that we have written in the case of position vector. So same thing we are doing here again, that this here also, this was hypotenuse. So hypotenuse square is equal to perpendicular square plus base square, and The tan theta is equal to perpendicular upon base, opposite upon adjacent. Same thing we are going over here. So tan theta is equals to opposite side, that is Vy upon Vx. So we have remembered the trigonometric ratios with like this way, but now we can further to learn them in better way. We can remember this as open, Adam open, hurry, Adam. So in our triangle, this was 90 degree, this was theta, so this was hypotenuse, this was perpendicular, this is base. Now here I can just say, if this is theta, then I can say this side as opposite to theta. So this is opposite to theta. This side remain hypotenuse and this side as adjacent to theta. So now it's better if we do remember sine, cos and tan with these ratios. So sine equals to opposite upon hypotenuse. This gives me opposite side is equals to hypotenuse sine theta, and cos theta is equals to adjacent upon hypotenuse. This gives me adjacent is equals to hypotenuse cos theta. So this was the one thing, this is second thing. And as I was talking about resolving of vector, so this Vx length, I can write it in terms of V. So this is the adjacent side to theta. So adjacent side is hypotenuse cos theta. So this is hypotenuse V. So Vx is equals to V cos theta. And Vy can be written as V opposite side is equals to hypotenuse sine theta. So hypotenuse V sine theta. So this is another important thing, that Vx can be written as, so Vx can be written as V cos theta and Vy can be written as V sine theta. So these are how we have written the velocity along x-axis, velocity along y-axis. So these are very important points. So we have done everything now. The magnitude, the direction, and so this was all about the average velocity. Now I am interested in the velocity at this particular point P. What is the velocity at P? So this was the velocity from average velocity when I moved from point P to P dash. So this was my average velocity that I have calculated while moving from P to P dash. Now I want to find out what is the velocity at P. So now I want to find out the velocity at P. So velocity at P, the particle was at P at time t. At time t, a particular time. So this velocity is known as instantaneous velocity. Instantaneous velocity. So again, instantaneous velocity is again a vector, and it definitely will have direction and magnitude. So what's the direction of the instantaneous velocity? So direction of the instantaneous velocity is always, the direction is tangential to this point on the curve. So I will draw a tangent, and this will be my direction of instantaneous velocity. So that's the direction. So direction of the instantaneous velocity is tangential at P, tangent at P. Now, what will be the symbol for instantaneous velocity? So just simply remove this bar. So, and that will be the symbol for the instantaneous velocity. So if you put a bar, then it will be average velocity, no bar, instantaneous velocity. So how do we calculate this instantaneous velocity? What actually I have done is I am just limiting. So here the total time was delta t between P to P dash. The time was delta t. We have already done this, that average velocity is displacement upon time, and time was delta t. So this is delta t time from P to P dash. Now I am interested in finding the velocity at P. So somehow I need to use this formula, average. I know the formula of the average, but how can I change this average to instantaneous? If I limit delta t tends to 0, if I keep on making delta t smaller and smaller and smaller and smaller and bringing it here, so this is delta t, so very little time, and more the you will decrease the time delta t, though, so the average will be better and better moving towards the instantaneous. So average will be more representing the instantaneous, as this delta t will be lesser. So that's how we get the instantaneous velocity. So how do we write it mathematically? I want delta t to be as small as possible. So as small as possible means I'm limiting delta t to 0. I want it to be near to 0, as near as possible to 0, approaching towards 0. Then only this average velocity that I was calculating will be, so this displacement definitely will be according to delta t, and I want delta t as little as possible. And then this instantaneous, when this delta t will be 0, limiting to 0, not 0, it is limiting to 0, it is nearing to 0 as far as possible, and better, this average will be the representative of instantaneous velocity. Now, how to write this in much better way? So this part I will be writing in differential form as d by d. So this thing, and this is dr by dt. So that's how in physics you need to remember that this step, how do we get this calculus, this differential, from where I have got this differential. So always remember this dd is limiting this denominator to 0. I have changed these delta symbols to dd. Okay. So that's my formula of the instantaneous velocity. So in average velocity, I will be simply finding, so in physics, whenever you have the formulas, if it involves this differentiation, then only it will be instantaneous. And if differentiation is not there, it means it is average quantity. So you can simply tell that it is average or instantaneous. For any physical quantity, it is valid. Like, I am giving you one example of, suppose work done is equals to, or you can say, let us take example of power. Power is equals to work done upon time taken. So another formula for power is dW by dt. Now tell me which one is average and which one is differential, or which one is instantaneous. So obviously this is average power and this is instantaneous power. So by just looking at the formula, you will be able to tell whether it is average or whether it is instantaneous. Now, simply the remaining formulas will be the same. Here we will be writing here limiting delta t tends to, like I have written here. Here also I will write, and as a result I will get here same formulas, but here these average sign will be removed, and so I will get this as Vx I cap plus Vy j cap. So here in this formula for average power, this can be like power average, and this would be simply P. So now we don't have, so here we had average, here also average, here also there's no average, no bar symbol. So simply that's the difference. Now same will be the magnitude, there is no difference. So same formulas for magnitude over here, there is no issue with that. So same formulas. So this was about average velocity and instantaneous velocity. So same, the direction as I've told is tangential, and the magnitude of velocity, instantaneous velocity, will of course be Vx square plus Vy square. So that's the component. And if this is I have got V. Now again I will its components, I will find its component along the x-axis and y-axis. So along the x-axis, this angle theta, so this is tangential, so that's I have got at this point on the curve. So here this tangent, this is I have drawn here this thing. So this thing I have brought over here. Okay, so this thing I have drawn over. So this will be this horizontal component of velocity will be, you can see here, so adjacent is hypotenuse cos theta, and this is hypotenuse sin theta. This is Vy, so this is Vx and this is Vy. So in terms of tan theta, I can write it as, so this is of course Vy, and this is of course Vx. This much is Vx and this much is Vy. So here the coordinates will be Vx and Vy. So simple. So tan theta is equals to Vy by Vx, and we can write tan theta as tan inverse Vx upon Vy. So this was the concept of velocity vector. Thank you so much for watching this video.